Okay, so in this video, we're going to talk a little bit about the properties of matter. So we can classify matter by states and composition. What else? Well, we can also start to distinguish matter based upon the properties it has. So a property of matter is a characteristic that is able to distinguish one substance from another. For example, if I had a glass of water and a glass of alcohol, I could definitely, if I smelled them, I'd know which one was the alcohol right away. You know, you could feel it burn a little in your nose, basically. So when we're looking at metals, for example, we're able to distinguish gold and silver by their color. So properties are kind of how we can tell different pieces of matter apart. So you could have a set of characteristics that we could use to tell two substances apart from one another. So I could look at my two substances, I could try to determine a characteristic that allows me to tell them apart. Or, for example, if I had a list of characteristics, I could choose a substance that has those characteristics. So that's what the properties can kind of be useful. If I need something that does something, I can look for it. Or if I have something and something else, I can start to tell it apart by leveraging the information in these properties. So that's how the properties of matter work. So for example, when we're talking about maybe a set of characteristics that we're trying to conform to, we might have a metal that I want to bend and shape to make a ring out of. So I'm looking for what's called a malleable metal. So that's a metal that's able to be bended and shaped. So I might go look for metals with different levels of malleability. So it held its shape on my finger, but I was still able to hammer it into shape. So we have two different types of properties in the end. We have a physical property and a chemical property. So a physical property is a characteristic that a substance displays without changing its identity. So if it's a physical property, you still have the same atoms and molecules you started with at the beginning as you do at the end. I like to think of it a little bit as how does a substance behave just when it's itself. So this might be something like color, density, volume, mass, melting and boiling points, and so on and so forth. A chemical property is a characteristic that a substance displays when it's changing its chemical composition. So when it's going from one form of a substance to another form of a substance. A chemical property is how I like to think of it behaves as it changes into something else. So I have something completely different at the end than the atoms and molecules I started with, a different composition. So this might be toxicity, chemical stability, flammability, reactivity, whether it's acidic or basic, so on and so forth. So that's just kind of talking about physical and chemical changes, but let's really get into the nitty-gritty about what happens. So if I'm just looking at a physical property, fine. But what happens if a physical property changes in our matter? So even if we're just observing the properties of matter, we can also observe how they change. So changes in matter are classified both into physical and chemical, meaning the same thing. So in a physical change, we start with the same thing we ended with. Or we end with the same thing we started with, and in a chemical change, we have something different at the end than what we started with. So, again, a physical change means a matter might change its appearance, but it's not going to change its chemical makeup. So, it might look different, but you still have the same thing in the end. So, it's just a different form. Okay, so it's the same thing, just a different form. So you might think about, crushing a can, or if we boil something, we still have the same thing. We might shred paper. If you mix sand and water, they don't really mix. It's just kind of a physical change then. We might melt ice, or you might break glass or something like that. So in our little picture here, we can see that we have liquid water down here at the bottom, all these little water molecules going up into the gaseous form of water. So it's the same thing at the start when it's water, and at the end when it's gas. So you can go ahead and take a look at this picture here and determine which one of these best represents when the molecules go from being liquid water and they vaporize into steam. So go ahead and pause, and then we'll talk through the answer to this conceptual checkpoint. Okay, so if we're looking at this conceptual checkpoint, we want to make sure we have the same thing at the end that we started with. So if we're looking at this, this means we have one red atom, two gray atoms all hooked together. It's a water molecule, one oxygen, to hydrogen. So I want to make sure my molecules look the same before and after, and then that they're more spread out because they're a gas rather than a liquid. So if I start down here, I see that I have all my little red and white separated, or red and gray separated. Well, that's not the same molecule I had here. That is a different substance. So this is not the same as this. So that means it can't be vaporizing into steam because it's only a physical change. If I take a look at this, I have 2 red ones and 2 white-gray ones hooked together. So if I look at my molecules here, this molecule does not look the same as this molecule, so therefore it is not the picture that best represents the molecules turning into steam. If we look down here at A, the first picture, we see that we have the same kind of molecule. We have 1 red, 2 white, 1 red, 2 white, and they're more spread out, which would better represent a gas versus these liquid ones are pretty close together. So our best representation in this case is going to be A. So we also have chemical changes in addition to our physical changes. So in chemical changes, matter is going to change its composition. So we have something different at the beginning and than we do at the end. So it may or may not be accompanied by a visual change. We may or may not see what's happening, but in the end, you do not have the same thing you started with. So this might be like burning wood, digesting food, cooking an egg, milk going bad, fireworks, mixing vinegar and baking soda, or chemical reactions. So we have the chemical change in matter. So here we see that we have a pure part that was just pure iron, and now that it's rusted, we have some red oxygen molecules in our iron. So it's taken on those oxygen molecules. So rust just happens when oxygen mixes with our metal, and so here it's a pure substance. Over here we have a chemical change. It's a different substance in the end. It went from being iron by itself to being iron oxide or rust. So here's a bonus conceptual checkpoint. Go ahead and take a look at this. Which one of these lighters, the one on the left or the one on the right, actually depicts a chemical change? Go ahead and pause, and then when you come back, I'll tell you why it works. So, that being said, if I go ahead and I take a look at the kinds of molecules I have in my lighter on the left and my lighter on the right, we've got the same thing when we're looking at the liquid in the bottom of the lighter. It's all liquid butane. So these are all the same kinds of molecules here. If we look at our lighter on the left, we have a butane molecule in the lighter. We have a butane molecule outside the lighter. So this looks like I have the same thing before, the same thing after. I think that one's a physical change. However, if I look at my lighter on the right, I see that I've got butane molecules in my liquid, and I have carbon dioxide and water molecules on the outside. See, I've got the black and the white here, that's butane. I've taken that butane, I've combined it with ambient oxygen in the air to make carbon dioxide and water. So if I look at this, I have something different here than I have at the end. So this means I'm going to have a chemical change. So you might notice this picture on the left, when we have liquid and gas, that would be just like pushing the button on the lighter, letting some of the gaseous butane out. However, if we strike the lighter and we actually hold a flame, that's when the combustion happens to change the liquid butane into these carbon dioxide molecules in water. So the last little bit we have to talk about here when we're talking about matter is the law of conservation of mass. So remember back when we were talking about the scientific method? Lavoisier's back. I'm not going to sing the Eminem song for you, but it was late at night when I was making these PowerPoint slides. You got a good joke in there. So just to be clear, the law of conservation of mass states that matter is not created nor destroyed in a chemical reaction. So things may get rearranged. We may have different kinds of molecules, but in the end, we still have the same amount of stuff. So during any chemical or physical change, the total amount of matter that we have remains constant. So we're not going to like all of a sudden have one of our atoms disappear and it doesn't exist anymore. No, in a chemical reaction, we are always going to have the same amount of matter that we started with. So it's the law of conservation of mass. We talked about it before. Remember, Lavoisier was like seeing if his reaction weighed the same before and after, even though he had a controlled experiment in a jar. And he determined that everything always had the same mass. So that's where the law of conservation of mass comes from. The law of conservation of mass is actually applied. So for example, I have a chemical reaction written out here. So often we talk about the reactants being on the left. They're the things we started with. We'd have our products at the end. They're the things we end with. So reactants on the right or left, products on the right. And we'll learn a little bit more about these. This is a pretty simplistically written one. We'll write them ourselves. But for right now, we're just thinking about what happens if we take some butane, we take some oxygen, and then what happens when we turn that into carbon dioxide and water. So for example, if we had a 58-gram sample of butane that would react with 208 grams of oxygen, and that would produce 176 grams of carbon dioxide and 90 grams of water. Well, when we check this out, we add 58 and 208, we get 266 grams, and when we add 176 and 90, sure thing, we get 266 grams again. So if we can figure out that we have the same amount of mass in the reactants as the same amount of mass in the products, that means the law of conservation of mass was demonstrated. It happened, it holds. So there was a chemical reaction occurred, but the same amount of mass in the end. So we have one last conceptual checkpoint to look through here. So if we have a drop of water, we put it into our flask, we seal our flask nice and tight, and we heat that droplet so that it goes from liquid to gas. Is the mass of that container and water together going to be different after heating, or will it be the same? So go ahead and pause, think about it for just a few seconds yourself, and then come back to me and I will let you know. So remember, this is just classically Lavoisier's experiment. You know, he took his jar, he heated it up, he saw what happened. So no, if the law of conservation of mass is correct, then the mass in the container is not going to be different before and after. It will be the same. So that's an application, again, of the law of conservation of mass. So same before and after. As long as it's the same before and after, the law of conservation of mass holds. If the law of conservation of mass doesn't hold, it's not a real chemical reaction. So that's a little bit about that.